Now, having noted that we still are really just beginning to learn about what sort of reasonable or appropriate security might mean for an AI system, there is some learning that's being done, and it's useful to walk through this NIST document, particularly for how it's kind of breaking down different kinds of adverse events that can happen at different stages. And if you take a look here in the NIST document, you see that in AI governance, we usually do talk about this training stage and then this deployment stage. And I think those terms should be pretty obvious to you, right? The system is being trained on some set of data, and then it is being rolled out into deployed into whatever use it is, whether it's internal to the developer of the system or whether it's external to customers or other third parties. So there are different kinds of attacks that can happen at these different stages of development. And looking back at this little graphic, I think the graphic maybe is a little overly complex, but you can get a feel for how these different sorts of problems might happen at some of these different stages. And one thing I want to point out about this graphic, and notice it's talking about availability, integrity, and privacy, I guess AIP. Now, when we talk in cybersecurity, we often talk about CIA, and that means confidentiality, integrity, and availability. And when we talk data security, we say data is only secure if it's confidential. If you keep it confidential when you want to keep it confidential. Now, you can keep data perfectly confidential by just deleting it, right? Or by encrypting it so that not even you can break the encryption. Now, that might be useful if you want to destroy or get rid of the data, but what we want is to maintain the integrity of the data, which means that whatever the data says, whatever values it's giving us, we know what those values are and they haven't been changed. So that, say the data is my name, Professor David Opterbeck, we keep it confidential, but not in a way that disables us from knowing that the data point is Professor David Opterbeck, that name. And then availability means that the data also has to be available to use in the way that it's meant to be used when it's necessary for it to be used. So if my name is in a customer database, then the vendor that's providing me the service has to know that it's me that has placed the order, and that they have to be able to do that right when they need to fulfill the order. So again, we can keep it perfectly confidential and encrypt it in a way that you have to go through steps that take a full day or a week to get the decryption keys, but that's not useful, right? So we want confidentiality, integrity, and availability for the full sense of data security. Now, I think part of what this breakdown is trying to do in this NIST document is to think in similar terms of what we want an AI system to do. So we want an AI system to be available for use in the way that it is meant to be used to do the beneficial things that it's meant to do. We want it to be to possess integrity, meaning that the system is functioning as it's meant to function, that it hasn't been compromised in some way, and that it's giving the kinds of responses with the degree of accuracy that we expect from that system. And we want the system to account for privacy. If the system has been trained on or is processing or managing personally identifiable information that is required to be and meant to be maintained as private, that it is still doing that and is still maintaining that privacy. So the way NIST is kind of framing this, I think, is playing off that CIA concept a bit, but thinking about availability, integrity, and privacy. So if we look at the section here on availability, you can see that some of these attacks are in the training stage. So these attacks on model poisoning and data poisoning here and here and here are really all about someone accessing the data or corrupting or injecting something into the data at that training stage. And if the attacker is able to do that, then the model is not going to be trained in the way that you anticipate that it's supposed to be trained, meaning there's a high degree of likelihood that it's not going to function as accurately and as fairly and so on as you expect it to. If we look at this energy and latency box here and query access, this is talking about something in the deployment stage. So this would be a circumstance where the model has been deployed, but there's an attack that is making the response very slow, so it's not effective in real time or close to real time as it's supposed to be, or is basically taking the system offline. So whereas model poisoning is really in a way new. I mean, not totally new, because a cybersecurity attack could corrupt data, but the purpose of it here is to corrupt the data to produce a different output. That's something new in AI. The kind of query access, that sort of thing, is not necessarily new. You can think of something like a DDoS attack in the traditional cybersecurity space, which is harnessing the power of, say, a bot that's many, many millions of connected computers to simultaneously send queries to a particular server in a way that overloads the capacity of that server and takes a website offline, right? A classic kind of availability attack when we're talking about cybersecurity. So, you can do similar things with even through, for example, DDoS attacks on the servers that are hosting an AI model. But other things like that, which are making the system not available and or making it not possible for a user to put in queries. As you read through the NIST document, for example, you see this kind of interesting dynamic where traditional cybersecurity and AI cybersecurity kind of come together, because, let's say you have your AI model here. I'll just kind of label it M. And then you have your application here. I'll label it A. And then, you have your device, whether it's a computer, a desktop computer, or a laptop, or a phone, or a tablet, or something else. And really, we could multiply this by different servers and other devices that might be in the cloud, right? And then we've got some software. I'll just kind of put S in the middle here, including APIs. Right, so it's not as a user. If I pick up my phone and I use Google's model or whatever, which it's not that great, so I don't really use it. But if we were going to do that, right, there's an application that I'm talking to. There's other software in the middle. There are APIs making calls on the operating system of my phone. There's other software involved in all these servers. All of those things could be compromised by traditional cybersecurity type attacks, and that could mean that my query is not getting to the model, and therefore it's not accessible to me, available to me, and or that my query is getting to the model in some corrupted way, so that I'm not getting those results. So those are examples of some of those kind of attacks at the availability stage. Now, if we move to this middle piece of this typology of integrity attacks, you can see that quite a few of these involve, again, poisoning or backdoor type things, where the data that the system is being trained on, either initially being trained on foundationally or iteratively as the system continues to learn, is being poisoned in some way. So, that can affect the availability of the system, meaning it just isn't usable at all, but it can make the system not unusable but not reliable, right? Not accurate and not reliable, and giving wrong answers, maybe in ways that are kind of subtle and a little bit difficult to detect as wrong, or maybe in ways that reflect biases that the attacker wants to bring forward, and that might be difficult to detect as actual flaws in the model. So similar kinds of things with model poisoning that can relate to the integrity of the system as it functions. But notice also we have these categories of evasion here. And these categories of evasion are really in the deployment phase of the model. And what this is talking about is the model is designed to do some specific function. So let's say it is an image recognition system, and it is designed to recognize in something that's being manufactured. This is just a remote for one of my lights here in my office, right? But let's take the top off of this and say the circuit board here is being manufactured, and they're making many of these, thousands of these run through the assembly line every day. And we don't have a human being with a magnifying glass checking every one of these things. That would be really inefficient and not very accurate. But what we have is a photo system that it's going through very rapidly, and an AI that has been trained to detect if there's some kind of very small flaw in the circuit board. And if the AI detects that flaw, it'll boot one of that flawed unit off of the assembly line. So a very common kind of application of image recognition AI systems. So an evasion attack of that sort might be designing some kind of defect in the board, in the circuit board, right, in some way that the system would fail to detect. And maybe it's hard to think of why somebody would want to do that for something like this controller, right? But think of a image recognition system that's doing quality control on a self-driving car component or on a military device component, something that's much more kind of important for public safety. And you can see that getting the quality control, be able to sneak something through that is designed and engineered in a way to avoid the image recognition system, evade the image recognition system, could be a real problem. Also in facial recognition systems, as another example, facial recognition is an image recognition system that's taking an image of your face, and that's then using the known kind of data points of the shape of an individual's face to compare it to existing data and make a prediction as to whose face it is, right? If it's your face or not your face. And so then evasion of that would be some way of manipulating the features of the face to avoid detection of the system. Now, that could be privacy protective in some way, and you might, from some civil liberties perspectives, you might think something like that could be beneficial in some contexts. It all depends, of course, on how we feel about the system and what it's being used for and civil liberties protections. But it's just another example of evasion of what the system is meant to do in its implementation. Another good example is, let's say, plagiarism detection software. Traditional plagiarism detection software that you might have come across at some point in your academic studies, like Turnitin, really in the past was just comparing your material to a hard database and trying to see if there were chunks of it that are literally lifted. Now, more sophisticated AI-based can be trained and sort of make some correlations as to how close something comes to what the system has been trained on. And so again, there might be techniques for constructing something that in fact is plagiarized but is meant to evade that sort of system, right? So all those sort of things are in this deployment phase. And the poisoning things are generally, well, many of the poisoning things are in the training phase. There are also kinds of poisoning attacks that could happen after the system is deployed if it is a system that is learning iteratively, and if the inputs that are given to the system are part of what is causing the system to be refined and hopefully be improved, right? So then there are ways of poisoning that are making the system learn in ways that are sort of corrupted, that change it. All right, and then this last sort of graphic here in the NIST thing is about these privacy violations, and most of these are going to involve something at the deployment phase. Now, of course, if you're in the training phase and you simply have training data that you are storing or accessing in some way, and in a more traditional cybersecurity attack, someone gets access to that training data, which contains PII, right? That's a privacy problem for your AI, and it overlaps very closely with just sort of a traditional cyber attack. So that could be encompassed here, but what this is more directly talking about is two things. So one is from the model itself, is it possible to extract PII, personally identifiable information, on which the model was trained? And we have seen numbers of instances in which researchers have been able to do exactly that. Now, if you talk with some people in the AI space, and if you listen to some of the things that, for example, OpenAI will say about ChatGPT, they'll suggest, well, that really, it isn't really possible to do that because, let's take my name, I'll try to we'll write my whole name, right? But there's my name on some document, and that document is going to go into this AI system for as training data. And so it's not that the system is memorizing my whole name, but it's breaking all of the text, if it's a text-based system, into tokens. So the name David will be there. The letters that make up my last name will be there, and those individual tokens are then changed into algorithmic weights. And what's actually retained in the system are simply innumerable amounts of these algorithmic weights. So it's not like it's not like a database that you can just query and say, is David Opterbeck in there? It's not the way a large language model works. But nevertheless, through clever prompt engineering, it has been demonstrated that even though things have been tokenized and then broken down algorithmically, that it is possible to reconstruct that some individual's personal information has been in the training set, and even to determine what that information is. So that's a kind of model extracting information from a model. Now, the kind of reconstructing or inference kind of attack is similar to that, but it's not necessarily literally extracting what has been tokenized in the model, but it's using really predictive techniques, right, AI type techniques, based on the information that will be responded to certain kinds of queries, to predict with some degree of confidence that some specific kinds of information was used in the model during training. And that might be personally identifiable information. It might also be things like intellectual property or trade secrets. So, for example, there are some companies that are kind of in patent-heavy industries that are nervous about research and development employees using AI in their work, because if you are querying the AI and you're giving the AI certain information about what you're working on, you may be disclosing a trade secret, or you may be triggering the statutory clock, called the statutory bars, that run for when you have to file a patent after making certain disclosures about an invention that you may have developed. It's entirely unclear right now in the law exactly to what extent like querying an AI might be a disclosure of a trade secret or triggering a statutory bar, and to what extent that information is, if it's being used to iteratively train the system, is then in the system. Because again, if it's training the system, it's being tokenized and broken into algorithmic weights. But if that kind of thing can be either extracted or predictively reconstructed, it might produce those kinds of problems. So we can see here poisoning of a model at a training stage. We can see, again, in the integrity aspect, poisoning of a model at a training stage. We can see these kind of evasion attacks. And I should have said, hiding information from the model itself or evading the safeguards of the model and causing the model to do things that it's supposed to be built to not be able to do. And then extracting from the model or reconstructing from the model PII or information about business and trade secrets. And if you read through the whole document, it gives you some possible mitigation strategies for many of these kinds of attacks. And some of these I think are fallback on, again, kind of traditional cybersecurity ideas. So in that training stage, of course, you have to use good data hygiene and security for any PII that's being used to train. You need to have good cybersecurity and make sure someone's not getting in and just exfiltrating that data. You need to subject the model to red teaming after it has been deployed and as it's being deployed to see what kinds of evasions and attacks can be done through prompt and query engineering. You need to understand the architecture of where your model is being housed and deployed, whether it's through the cloud or whether it's locally or a hybrid of both of those, and how vulnerable any of those things are to like a DDoS attack or something else like that might make the model inaccessible. And you have to do ongoing monitoring to make sure that the results that the model is producing are the kinds of results that you expect and hope that the model is meant to produce. And if you find that it's not producing those results, then you've got to have a set of metrics and a system in place to be able to try and figure out why is that happening and how can we correct it. It may simply be model drift, which just happens as a model learns. So it's not anything nefarious, but it's still something that has to be corrected through recalibrating the model. Or it may be that there has been some poisoning of the data. And in that case, your governance structure hopefully will have included documenting the steps you've taken in the training to be able to kind of reconstruct where and how the model might have been poisoned and how to remedy that. So very much some traditional cybersecurity practices and concepts, some new things with AI, some things that we're learning about, that we're thinking, we have some mitigation strategies for, but a lot of things where we just really don't know exactly how the best practice, compliance, and legal standards are going to develop.